Hi class. This is the video for Module 8, and I'm going to just go through the notes. These are annotated on Blackboard, but I wanted to go over them and annotate them as I go. So we're going to work towards finding a confidence interval for a population proportion. We did a little bit about that in Module 7, but in this module we're going to talk about what happens when we don't know the population proportion. So we're going to start off talking about examples that says, suppose the actual proportion of TCC students who have a pet is 30%. That's our parameter, P. So we have that P equals 0.30, which is the mean of our P hats. And we don't know what our P hat is because we haven't taken our sample yet, but we're going to do a sample of size 80, that says. But we also need our standard error or standard deviation of P hat, so I'm going to write the sigma of P hat, which is the same thing as the standard error of P hat, which is the square root of 0.3 times 0.7. That's your P times your 1 minus P over 80. And then I'll bring in my calculator. And calculate that. Clear that out. So I have second, and the x squared q to get square root, and I do 0.3 times 0.7 divided by 80. Close parentheses, enter. So my standard error is about 0.051. That's funny. We'll say it's about 0.05. That's close enough for now. All right, and then now I can say the interval that contains 95% of all sample proportions, if you remember your empirical rule, would be 2 standard deviations to either side of the mean. So that would be mu sub p hat plus or minus 2 times the standard error of p hat, which would be 0.30 plus or minus 2 times 0.05, which is 0.10. So that would be 0.20 plus or minus, I missed my minus, 0.20 to 0.40. That would be my error. So 95% of all sample proportions will fall between 20%, we'll say somewhere between 20% and 40% of students in that sample have a pet. All right, so let's look at the next question here. It says if the sample proportion lies within that interval, a similar interval, 2 standard errors in either direction from the sample proportion would contain the population proportion. All right, let's show that. All right, what does that mean? So that means if we have our normal curve, our bell curve, okay, so we've got here, we got 0.30 in the middle, and over here we got our 2 standard errors to the right is 0.40, and our 2 standard errors to the left is 0.20. And here is 95% of p hats are in this range. All right, so if a p hat is in that range and I go 0.10 on either side of that p hat, then 0.30 will be within that. What does that mean? That means if p hat is within 0.30 plus or minus 0.10 or 0.20 comma 0.40, then 0.30 is in p hat plus or minus 0.10. Basically, it's saying if your sample proportion it falls in that within 0.10 or within 10% of the population proportion 0.30, then the reverse is also true, that the population proportion lies within 0.10 of the sample proportion. Or sorry, the population proportion lies within 0.10 of the sample proportion. All right, so the formula then would be just p hat plus or minus the 2 times that standard error formula, p times 1 minus p over n, the square root of all of that. In this case, that was p hat plus or minus 0.10. So that's what we could use. So 95% of the time, that range of values would capture the population proportion. Well, what assumption does this formula make? First of all, it assumes, excuse me, it assumes that p hat is normal. In other words, i.e. that NP is at least 10 and n times 1 minus p is at least 10. In this case, that's fine because our n was 80 and our p was 0.3, so that's 24. And our n and 1 minus p would be 0.7, and that would be 56. And so those are both greater than 10, so that's fine. What does the 95% of tell us? That 95, well, let me start that differently. For 95% of samples of size n equals 80, p will fall in the sample proportion from that sample plus or minus 0.10 or p hat plus or minus that 2 times the standard error of p hat. That's that formula. Okay, what's the big problem with that formula? Well, two things. First of all, well, the main thing is we don't know p, the population proportion. Oops, excuse me. And the whole point of doing a confidence interval is to tell us where we think p is. So we generally don't do it if we know what p is. Now, in this example, in this particular example, I hypothesized that p was 0.30, but usually we don't know that. How can we solve this problem? Well, what we're going to do is we're going to substitute p hat for p in the formula. Okay, p hat is an estimate for p, so we'll substitute for p. How does this change our assumptions? Well, instead of np and n1 and minus p, those are the assumptions we need. We check n times p hat and n times 1 minus p hat, which is the number of successes and failures in our sample. So if we don't even need to actually do the calculation if we're given the number of successes, but if we're just given the proportion of successes, then we do need to do that calculation. So if there are at least 10 successes and at least 10 failures in our sample, then we can use the normal distribution. All right, so our new formula becomes, let me give myself a little bit of extra space here. Our new formula is now p hat plus or minus 2 times the square root of, instead of p, I'm going to put a p hat there, and 1 minus p hat. But the n doesn't change because that's the sample size, and of course I always know my sample size because I took my sample. So very, very similar. You're just substituting the sample proportion in the formula for the population proportion. All right. So now we say, okay, suppose we conduct a survey of 80 TCC students and find that 26 of them have a pet. Calculated 9. So now we're no longer assuming that we know 30% of the population have a pet. So it says create a 95% confidence interval for the proportion of all TCC students who have a pet. So let's pull up my calculator. Oops, it's down here. Let's calculate my sample proportion. My sample proportion was 26 out of 80, which is 32.5%. Okay, so p hat equals 26 divided by 80, which equals 0.325. So to find my confidence interval, what I'm going to do is take 0.325. I'm going to add and subtract 2 standard error. So 2 times the square root of 0.325 times 1 minus 0.325 over my sample size of 80. Now the nice thing is the calculator, well, I don't have to type all that in twice. What I'm going to do is I'm going to type in, let's bring my calculator over here, and I'm going to type in 0.325. I'll usually do the minus first. So I type minus 2 times, get my square root, second in the x squared key, 0.325, open parentheses, 1 minus 0.325, close parentheses, divided by 80, close the parentheses for the square root, and hit enter. So the lower end of my interval is about 22%, 22.0%. I forgot to close my parentheses back here. All right, bring my calculator back up. Now, rather than typing this whole thing over again, I can just hit second and the enter key, and I get the exact same thing I just typed. And I can go up and over to where the minus is and change that to a plus. And I hit enter. Oh, it didn't like whatever I did. Maybe I hit the plus in the, yeah, I hit the plus in the wrong place. So I need to hit second and enter. Go over. I'm getting a lot of emails today. My apologies for those popping up in the way. All right, change that to a 5 plus. There we go. And I get 0.4297, which would be to 2 decimal places, which is fine, 0.430. So my confidence interval is 0.220 to 0.320. I think it was. Oh, no, 0.430. Sorry about that. Sometimes you gotta remember a little better. 0.430. Okay, so that is my confidence interval. What does that confidence interval mean? Well, it means we can be 95% sure that between 22.0% and 43.0% of all TCC students own a pet. Okay, so the 32.5%, here I'll rewrite this as 32.5%. That's telling me that 32.5% of my sample own a pet. But what we're really interested in is the population. So I want to know what does that information tell me about the population, and what it tells me about the population is that between 22 and 43% of all TCC students own a pet. So, or you could alternatively say, since this is about a proportion, it said the proportion of all TCC students who have a pet, we could say we can be 95% sure. We can also replace that word sure with confident. So I'll put in here above or confident. We could say that the proportion of all TCC students who own a pet is between 0.220 and 0.430. Okay. What does this mean? What does 95% sure mean? It means this method captures the parameter. In this case, the population proportion is what the parameter is, 95% of the time. I don't know if this is one of the 5% or one of the 95%, but 19 times out of 20 it gets it right. Now before you may say, well, it did capture 30%, but the 30% was just a guess. It said suppose. So if these were the data, then I would be pretty sure that the proportion that own a pet is somewhere between 22.0% and 43.0%. All right. How about doing this with technology? Okay, it's actually really easy to do this on the calculator. Let's go to our calculator. We hit stat, and then we go over to where it says tests. And it's a little ways down. This is not a test, it's an interval. It's a confidence interval, and you see number 7 says interval. So I can scroll on down past, it's not a Z interval. It is a 1 proportion Z interval is what it's called. So letter A. So if I hit enter once I get down there, or you can just type the letter A, we're using the alpha key on your calculator. X is the number of successes, so I hit 26 for X. In other words, in this case, the successes are people who, each success is a student who owns a pet. This N is the sample size, or 80, and then the confidence level is just 95%, or 0.95. The calculator will accept either 0.95 or 95%, or 95. Hit calculate, and I got a slightly different answer, okay? And I'll explain why I get a slightly different answer, but that's okay. It's quite close to the answer, within 0.2%. So that's not a big deal. So let's write the directions here, because that way, but you can go back and rewind the video to watch what I did. So I hit the stat key, and then went over to the tests heading, and then I did let's put the letter there of A that I went to. I went to A, which was 1 prop Z int, and then X for X was the number of successes. And N was the sample size, how many were in my sample, and then N is my, not N, sorry, C level is just my confidence level. And you'll see there that that just below there, that was, it says 99% confidence. So in some cases I might change that. So actually we'll go and we'll go back. I'll hit stat and test and go down to A, and I'll do a quick screen capture and put it on the video here on the notes, and maybe I'll even replace the notes that you have. Oop, I didn't go all the way over to tests. I'll replace the notes you have with these notes, perhaps, if I have the opportunity to do so. There we go. So let's real quick screen capture that, paste it into the notes. Okay. Oop, didn't mean to do that. There we go. Make that a little bit smaller. Something like that. Okay, let's see if I can do. There we go. All right, and then after I do that, go back here, go back to my calculator, hit enter, and then you can see what entries I have substituted in. All right, copy that, paste that, smaller. There we go. And then it spits out the answer. Maybe I need to give myself a little more space here. Let's go ahead and hit enter. And then we can copy this last screen. Okay. Now, I'll show you in just a minute why this number is different. All right. So let's just take my pen and point. There we go. All right. So, well, that 2 in the formula is what would change if we wanted a different confidence level. So the formula is this, p hat plus or minus. And the actual more general formula is z star, and I'll explain why we put a star there, but that's a z-score, times the square root of p hat times 1 minus p hat all over n. Okay, so what is this? So p hat is just, p hat's what we've been using, but this depends on the confidence level. And it's just basically, depends on confidence level. how far out you have to go in a normal distribution to capture whatever percentage of the data. And we know based on the empirical rule that if we go out 2 standard deviations or standard errors, we capture 95% of the data. Well, it turns out that that's actually partially correct. That's an approximation. A more exact number is 1.96. And if we use 1.96 instead of 2 in our formula, we would have gotten answers closer to these that you see on the right of 0.22 and 0.428. In fact, we would have gotten those almost exactly. We'd have been a little off because even 1.96 isn't exact. It has many decimal places. So we change the z star, or of course you can just change the C level on the calculator. So I'm going to write under here, but really just change C level on the calculator. You'll see on OLI that it actually gives you the Z star for the various confidence levels. The most common are 90%, 95%, 99%, 95% being certainly the far most common. But for example, the Z you would use for a 99% confidence level would be 2.576. And for a 90% confidence level, it would be 1.645 because you need to go further out to capture more of your data to be more sure, to have a higher confidence. All right. Now this confidence interval, let's go back 1 second to the previous page. This final confidence interval we created down here, we say that it consists of 2 parts, and this is true for every confidence interval. The first is just the part, the p hat. This is our point estimate for our parameter. So let's see, point estimate for parameter. In this case, the parameter is p, the population proportion. And then the second part, this is called our margin of error, what comes after. Now, the reason I note that, one of the reasons I note that is because, of course, you'll see it in various places. The other reason I note it is because you may have seen polls and it might say something like the margin of error is plus or minus 0.03. And so that's exactly what it says. That's what the margin of error is. It comes from a confidence interval. Okay. So in this particular problem, the margin of error is how much I had to go up or down from 0.325. And the answer is I had to go up 0.105 and down 0.105. You could do a quick subtraction to check that. Or just do the part of the formula after the plus minus. So the margin of error is about 10.5%, which is pretty high, but that's because we did a small sample size. As you increase your your sample size, your margin of error will decrease because you should get a more accurate answer with a larger sample size. All right, so the z-score for the 99% confidence interval is z star. Sometimes we do that and write 0.99 down below it, and I should say that's approximately, as I said before, 2.576. This is on OLI. Z star for 0.90 is approximately 1.645, and the Z star for 95% confidence is approximately 1.960, so 3 decimal places. All right, to reduce our margin of error, we could increase sample size, as I just mentioned, because bigger samples should have more accurate results, and thus I should be able to use a smaller margin of error. Increasing the sample size reduces the margin of error. All right, okay. A research company states that the confidence interval for the proportion of all college students who smoke is 0.21 to 0.28. It says give the sample proportion and margin of error based on this confidence interval. Well, the sample proportion of any confidence interval is right in the middle because we start in the middle, we go plus and minus. So how do I find the midpoint of 2 numbers? I just average them together. So I can do 0.28 plus 0.21 over 2. So if I take my calculator, in this case, I either need to use parentheses or just hit enter first, so I might do that. 0.28 plus 0.21, hit enter, and then divide by 2, hit enter. Oop, I missed the divided by, so I can do 0.49 divided by 2, and I get 0.245. So equals 0.245. That's halfway between 0.21 and 0.28. So that's also the other way you can do it. If it's pretty easy to figure out the midpoint, you could just figure out the midpoint. And the average of two numbers is always the midpoint between those. And then the margin of error is how much do I have to go up or down? Well, I can do 0.28 minus 0.245, or I can do 0.245 minus 0.21, or I can subtract 0.28 minus 0.21 and divide by 2. And all of that gives me the margin of error. I think they use capital M on OLI, but it's not really important what you use, but 0.035. You can see that the difference between the two endpoints is 0.07 or 7%. Oops, that should be 0.035. So in this case, 3.5% would be half of that. And then if we want to interpret, as I mentioned, the confidence interval, what I do is I say we can be, based on this particular sample, we can be 95% confident that between 21% and 28% of all college students spoke. So that should give you a pretty good background in confidence intervals. I believe that's the last page of these notes. Yep. So I'm going to do the rest of the notes. Let me go back down so you can see that. I'll do the rest of the notes in a separate video so that the single video is not too long. I hope this was helpful. If you have any questions, please send me an email or post to Piazza. I will also have the regular question and answer webinar next Monday. Right? Enjoy your weekend. Take care.